So we remember that the periodic table of the elements is arranged by the atomic number. The atomic number also tells us how many protons are present in that atom. And we're going to look at oxygen for this example, and we're also going to look at hydrogen. Okay, oxygen has an atomic number of 8. Hydrogen has an atomic number of 1. So let's move over so we can draw some stuff on the whiteboard. Let's start with our oxygen. Okay, we decided that it has an atomic number of 8. So what we want to do is to draw the Bohr's model of the atomic structure. So we need to remember what types of subatomic particles we have. So what are the parts of an atom? We need to have protons. We need to have neutrons. And we need to have electrons. Okay. We remember that protons are positively charged, neutrons have a neutral charge, electrons have a negative charge. Protons and neutrons are in the atomic nucleus. And then electrons orbit the nucleus in valence shells. Okay, so if our oxygen, okay, we know it has 8 protons. We don't really actually care about neutrons, so we'll ignore them for right now. And in order for it to be a neutral charge, if we have 8 positive charges in the nucleus, we know that we're going to also have 8 electrons. Okay, now we have to talk about the octet rule. Okay, the octet rule states that the outermost valence shell is going to be the most stable when there's 8 electrons present. And for every rule, there's always an exception for the rule, except for the first valence shell. I'm just gonna do VS. Can hold only 2 electrons. Okay, so as we're drawing our oxygen, I'm gonna make my electrons in red. So we're gonna have 1, 2. That's as many as that first valence shell can hold. Okay, but we need to have 8 total. Okay, so we got 2. We're going to go 3, 4, 5, 6, 7, 8. Now, we have 2 spaces where electrons could go. So the octet rule for this oxygen atom is not satisfied. Okay, there's a couple of ways that we could solve this problem. We could get rid of 1, 2, 3, 4, 5, 6 electrons, or somehow we could pick up 2. Okay, for this discussion, we are going to talk about covalent bonds where we are going to share electrons. So let's pull our hydrogens over. Okay, and our hydrogens have 1 proton in the nucleus. In order for it to be negatively charged or neutrally charged, it needs to have let's bring one of our hydrogens over. It has 1 positive charge, or 1 proton. For the atom to be neutrally charged, it's going to have 1 electron in its outermost valence shell. And so what we can see is that this hydrogen atom is also not satisfied. So what we can do, I'm going to redraw my hydrogen here, is draw that valence shell. And now this hydrogen atom has 1, 2 electrons in its valence shell. So its octet rule is satisfied. Okay, same thing we're going to do down here is we're going to fill that empty slot in the oxygen with one of those electrons from one of our hydrogens that are now sharing electrons. Okay, that's our covalent bonds, where we have shared electrons in our valence shells to satisfy the octet rule. Other ways that we can satisfy the octet rule include ionic bonds, so if we look at sodium, it has an atomic number of 11. So what we are going to do, if I just draw this out real fast, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 electrons. We could gain 7 electrons to fill this outermost valence shell, or we could just get rid of 1 electron and have it just be floating out here all by itself. Okay, this means now that there's 11 positive charges in that nucleus, but only 10 negative charges. Okay, that means that our sodium ion is going to be positively charged. Okay, if we look at chlorine, just make sure that y'all can still see what I'm drawing here. Move it down a little bit. Okay, chlorine has an atomic number of 17, so there's 1, 2 electrons, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, so now in our outermost valence shell, we have 7 electrons. So this electron that was given up by our sodium can come and hang out and fill that last spot in the chlorine's outermost valence shell. That is going to have 17 positive charges, but 18 negative charges. So then our chlorine is going to have an overall negative charge. When we have particles that have opposite charges, they're going to be attracted to each other. So our sodium chlorine, your table salt, is an example of an ionic bond. Okay? All right. Let's go back and talk some more about covalent bonds. Because we can have 2 kinds of covalent bonds. Let me find my eraser. Put that up there. All right, our covalent bonds, we can have equal sharing of those electrons, and we can have unequal sharing of electrons. Okay, when we have equal sharing of electrons, we call that non-polar covalent bonds. Okay, these are examples that we talked about are carbon dioxide. We talked about atmospheric carbon, 3 covalent bonds. We talked about atmospheric oxygen. Okay, all of those things. The other one that were really important that we need to talk about are fatty acids. Okay, so fatty acids are all of these carbon atoms that are held together in this big long chain that have hydrogens on them. The difference in the the attraction between carbon and hydrogen for those electrons is about the same. So as those electrons are zipping around, they're going to be spending their time equally between the hydrogen nucleus and the carbon nucleus. Okay, so there's an overall neutral charge. Okay. When we have things that are nonpolar, they are going to be hydrophobic. Okay. They are going to not dissolve in water, right? We are used to thinking about how oil and water do not mix. That is because the oil is composed of fatty acids. Fatty acids are made of nonpolar covalent bonds where we have equal sharing of electrons between the atoms that compose that molecule. In the case where we have unequal sharing of electrons, I'm going to make it black so it's easier to see. Okay, that is going to lead to a polar covalent bond. So let's go back here to our water molecule that we drew. We have a difference in the amount of attraction between the nucleus of the oxygen atoms and the nucleus of the hydrogen atoms if you're an electron. Okay, so in our hydrogen atoms, we drew our hydrogen electrons as blue, so I'm going to use blue for this. Okay, this hydrogen, this electron in this hydrogen atom can be zipping around the hydrogen nucleus, but it's also going to spend a lot more time of its orbit going around the oxygen atom. Okay, now because oxygen is being greedy and taking that electron more than what the hydrogen is getting, it's going to have a partial charge. And remember, we talked about this little fancy letter D. Because that electron is over there, that oxygen is going to have a partial negative charge because it has that extra electron. Over here, for both of our hydrogens, they are going to have a partial positive charge because that there's only a proton left. Okay, when there are electrons over here, there's only a proton left over here. Okay, giving it a partial positive charge. All right, that means it's going to have, our water molecule is going to have a negative pole and a positive pole. So we are going to call it a polar molecule. Good? Okay. When we have a polar molecule, they are going to form hydrogen bonds with water, and that is going to make them hydrophilic. Okay. An example of that is our glucose molecules. Okay. I'm running out of space on this board, but if I draw the chemical structure of glucose, something like this, we've got all these carbons here, and there's one over here. Oops, that's an H. Okay, and all of these carbons have an OH group on them. And we know that whenever we see an OH, we know that bond between an oxygen and a hydrogen is going to be a polar bond. The other one that we need to know is, so let me write OH is here. Okay, that's going to create a polar bond. And the other one is a nitrogen bonded to a hydrogen. Okay, that is going to also give us polar bonds. Okay, so when you're looking at a chemical structure of something, if you see an OH or an NH, you're going to be like, polar. Polar, like water, is going to be hydrophilic. So I also got a question of, how do we know if something is hydrophilic or hydrophobic? By looking at this chemical structure. Like, what are our clues? Okay, and we are going to be hydrophilic if we have a charged particle, okay, and that can be positive or negative, it doesn't matter. So what we're going to look at is if these water molecules, right, and we remember that our oxygens have that partial negative charge, if they interact with something that has a positive charge, like our sodium ion, they are the electrostatic attraction between our partial negative charge is going to want to interact with the partial positive charge of our sodium ion. Okay. If we have a chlorine that's negative, what we're going to see is a partial positive charge of the hydrogens are going to be interacting, backwards, with the chlorine. Okay. This is why water is called a universal solvent, because it can dissolve most things. Okay, water can, so whether we have a positive or a negative charge, hydrophilic. The other thing that we're going to be looking for is if a molecule is a polar molecule. Okay, so let me draw a glucose again. The bendy parts, there's a carbon that goes over here. This is an OH. Here's an OH. Here's an OH. OH goes down. And there's some other hydrogens, but we don't care about them. Okay. Now you guys know that whenever we see that OH, we know that that is going to be a polar bond that is going to allow our water molecules, I'm going to draw them blue this time, to interact. The partial positive side of our water molecule is going to interact with the partial negative side of this oxygen in our glucose molecule. Okay, they're going to be surrounding that. On this partial hydrogen, that's going to be surrounded by the partial positive oxygen of our water molecule, and so forth. So we can see with sugar, we have a lot of opportunities to form those hydrogen bonds, and so it is going to readily dissolve in water. All right, so now we can talk about what has to happen for something to be hydrophobic. The only way that we're going to have a hydrophobic molecule is if it has non-polar bonds. So again, I've drawn my fatty acid chain here, and what we're going to see, we're going to be looking for oxygen bound to hydrogen or nitrogen bound to hydrogen. And when we look at this chemical structure, we don't see any of those. And also, this has a neutral charge. Okay, so let's put that on our list. So when water comes around and tries to form hydrogen bonds with this, there's no place for the partial positive hydrogens or the partial negative oxygens to interact with this molecule. So there's no hydrogen bonding that occurs between nonpolar, uncharged, neutral charged molecules. Therefore, it cannot interact with water, therefore hydrophobic.